So welcome to my channel. Myself Raghunaри. I am studying in Sri Venkateshwar College of Engineering, Bangalore. Semester second, section Infinity. Course name Mathematics for Trivial String. Course code BMATE 201. Today's topic is about application of Lagrange inverse interpolation. Applications of Lagrange inverse interpolations is a powerful mathematical technique with numerous applications in various fields including engineering, physics, and numerical analysis. This section will explore the key applications of this important concept, showcasing its versatility and highlighting the reason for its widespread use. Solving nonlinear equations. Root finding. Lagrange inverse interpolation can be used to efficiently solve nonlinear equations by finding the roots or zeros of the equation. This is particularly useful in problems where the explicit form of the equation is not known or is difficult to work with. Parameter estimation. In parameter estimation problems, Lagrange inverse interpolation can be employed to determine the values of unknown parameters in a nonlinear model by fitting the model to experimental data. Inverse function determination. When dealing with complex nonlinear functions, Lagrange inverse interpolation can be used to determine the inverse function, which is often crucial in various applications such as signal processing and control systems. Numerical integration and differentiation. Numerical integration. Lagrange inverse interpolation can be used to develop efficient numerical integration schemes such as the Gaussian quadratic method, which are essential for computing definite integrals in various scientific and engineering applications. Numerical differentiation. Similarly, Lagrange inverse interpolation can be employed to derive accurate numerical differentiation formulas, which are crucial for computing derivatives of functions, especially in cases where the analytical form of the function is not available or is difficult to work with. Function approximation. By using Lagrange inverse interpolation, it is possible to approximate complex functions with simpler polynomial expressions, which can be advantageous in computational and analytical tasks where the original function is too complex to work with directly. Interpolation and extrapolation. Interpolation. Lagrange inverse interpolation is widely used for interpolation where the goal is to estimate the value of a function at a point between known data points. This is useful in various applications such as data analytics, signal processing, and curve fitting. Extrapolation. Additionally, Lagrange inverse interpolation can be employed for extrapolation, which involves estimating the value of a function at a point outside range of known data points. This is particularly helpful in predicting future trends or estimating values beyond the available data. Error analysis. When using Lagrange inverse interpolation or for interpolation of or extrapolation, it is crucial to understand and quantify the associated errors, as they can significantly impact the reliability of the results. Careful error analysis is essential for ensuring the accuracy for the final estimates. Optimization and decision making. Non-linear optimization. Lagrange inverse interpolation can be employed in non-linear optimization problems where the goal is to find the optimal values of decision variables that maximize or minimize a given objective function. This is particularly useful in engineering design, resource allocation, and financial modeling. Decision support system. In decision making processes, Lagrange inverse interpolation can be used to develop sophisticated decision support systems. These systems can incorporate complex models and data to provide insights and recommendations, aiding decision makers in various domains such as business, healthcare, and public policy. Inverse optimal control. Largest inverse interpolation also finds applications in inverse optimal control problems where the goal is to determine the objective function or cost function that best examples the observed the behavior of a dynamic system. This is useful in fields like robotics, aerospace, engineering, and economics. Inverse reinforcement in learning. Similarly, Largent's inverse interpolation can be employed in inverse reinforcement learning, where the aim is to infer the reward function that best describes the observed behavior of an agent, such as human or an artificial intelligence system. This has implementations in areas like human robot interaction and behavioral economics. Processing and image reconstruction. Signal reconstruction, Largent's inverse interpolation is a very valuable tool in signal processing where it can be used to reconstruct continuous time signals from a discrete set of samples. This is a crucial in applications such as audio and video processing where the original continuous time signal needs to be recovered from a finite set of discrete measurements. Image reconstruction. Similarly, Largent's inverse interpolation can be employed in image reconstruction where it is used to estimate the values of pixels between known data points. This is particularly useful in applications such as image scaling, super resolution, and medical imaging, where high quality image reconstruction is essential. Sparse data interpolation. Largent's inverse interpolation is also beneficial in situations where the available data is sparse or limited, as it can be used to estimate the values of missing data points. This is valuable in fields like geophysics, climatology, and astrophysics, where the acquisition of comprehensive data can be challenging. Biomedical and scientific applications. Medical imaging. Largent's inverse interpolation finds applications in medical imaging where it is used to reconstruct and enhance images obtained from various modalities such as X-ray, CT, MRI, and ultrasound. This helps improve the quality and diagnostic accuracy of these imaging techniques. Bioinformatics. In bioinformatics, Largent's inverse interpolation is employed in the analysis of biological data such as DNA sequences, protein structures, and gene expression profiles. It enables researchers to estimate missing data, perform curve fitting, and model complex biological phenomena. Scientific modeling. Largent's inverse interpolation is also used in scientific modeling and simulation where it helps researchers to approximate complex physical, chemical, or environmental processes. This is particularly useful in fields like fluid dynamics, material science, and climate science. Emerging applications and future directions. Machine learning and AI. Larger inverse interpolation can be incorporated into machine learning algorithms, enabling more accurate function approximation and enhancing the performance of predictive models in areas such as imaging recognition, natural language processing, and recommender systems. Quantum computing. As quantum computing continues to evolve, Largent inverse interpolation may find applications in the simultaneation of quantum systems, the optimization of quantum algorithms, and the reconstruction of quantum states from limited experimental data. In- Internet of Things. In the context of IoT, larger inverse interpolation can be used to estimate and interpolate sensor data in distributed systems, enabling more accurate monitoring, control, and optimization of complex IoT applications. Cybersecurity. Largest inverse interpolation can be leveraged in cybersecurity applications such as the detection of anomalies and the reconstruction of network traffic patterns, contributing to improved intrusion detection and risk management. Thank you for watching.